Good morning and welcome to the webinar. This is a Conservation Applied Research or CARD webinar, and it's going to discuss the savings and efficiencies of racked tankless water heaters. Thanks so much for joining us today. I'm Mary Sue Lobenstein, and I'm the Energy Conservation and Research Planner at the Minnesota Department of Commerce, Division of Energy Resources. In that role, I identify and analyze gaps within utility conservation improvement programs and coordinate and plan research to fill the gaps. The CARD program is a major tool of that work. With me today is Laura Silver. Laura is a senior state program administrator at the Department of Commerce, where she reviews utility conservation improvement program triennial plans and annual status reports. Laura was the project manager on this research and will be moderating the Q&A portion of the webinar. Our presenters today are Rich Srozena and Alex Hayner. Rich is a senior engineer and operations manager at the Gas Technology Institute, where he applies engineering research and best practices to standards writing, code development, product development, and market transformation. He was the principal investigator on the CARD project being discussed today. Alex, in his role as a senior research engineer at the Center for Energy and Environment, conducts research on emerging technologies in residential and commercial HVAC systems, with a focus on field instrumentation and on data analysis. Alex's recent research includes cold climate air source heat pump efficiency, rooftop unit optimization, tankless water heater efficiency, and commercial boilers. It's really great to have Rich and Alex here today to discuss the results of their research on tankless water heaters. Before we start, I'd like to go over a few housekeeping basics. All attendees will be in listen-only mode. We'll answer all questions at the end of the presentation, but as questions occur to you, we encourage you to type them into the Q&A box and send them to all panelists. We'll do our best to answer all questions within the time allocated, but if for some reason we don't get to some, we'll answer them after the webinar. This webinar is being recorded and will be available on the department website. The slide set from this webinar will also be available. This webinar is one in an ongoing series that are designed to summarize results from research projects that are funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. About $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to help enhance their energy efficiency program designs within their CARD or Conservation Improvement Program portfolios. As you can see by the pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is in the multifamily sector, but has implications for the commercial sector as well. It will discuss results from a recent CARD project that installed 2 condensing tankless water heaters in multifamily buildings to determine savings potential and possible drawbacks. Now I'm going to turn it over to Rich for today's presentation.
Thank you, Mary Sue. Good morning, everyone, and welcome to the webinar. And this morning we'll be discussing the demonstration of packaged central condensing tankless water heating systems in multifamily buildings. As Mary Sue mentioned, I'm a senior engineer with GTI Gas Technology Institute and presenting with Alex Hayner with CEE, Center for Energy and the Environment. I'd like to acknowledge the financial support of Minnesota CARD and the technical support from Laura Silver and Mary Sue Lobenstein. And our technical partner at CEE, we worked there with Alex and Ben Schoenbauer. And on the GTI side, the engineers were Mike Messenger Jr. and Paul Glanville. I'd also like to acknowledge the financial support from GTI utility members of the UTD group. And many of you may know of tankless water heaters. So instead of storage type heaters. They are tankless, and one's through system that typically heats the hot water through a heat exchanger with natural gas or other type of fuel. And the units we'll be looking at today are the condensing type. So they are most efficient in that they give up the heat that's released during the condensing process. And that may be in the order of 1,000 BTUs a pound of water or so. And it operates, and by doing that, it operates at cooler fluid temperatures and allows for additional energy gains. This particular project will look at combining these single units into a 4-unit gang and a 3-unit gang for the necessary capacity in 2 residential multifamily applications. So the single units can be mounted on a rack, which is what you see in the middle lower picture, or they can be mounted on the wall, which you see on the right. The research project was essentially a demonstration of 2 combined condensing water heating systems, replacing 2 tank systems in multifamily buildings in the Twin Cities area. And part of this project was to develop an assessment tool by applying best practice calculations and field data. And then the outputs of the tool could apply to parameters within similar building types based on occupancy, number of rooms, etc. The 2 baseline sites had tank systems and were monitored between 277 and 311 days. The 2 combined tankless water heating systems were monitored between 247 and 276 days. The hot water usage in these buildings were between 22 and 28 gallons per unit per day. Field site number 1 was in the St. Paul area, and it was essentially a 23-unit rental apartment building built in 1968. The building had both 1 and 2 bedroom units. Field site 2 was also in the St. Paul area, and it was a 17-unit rental apartment building built in 1970. The building had both 1 and 2 bedroom units. The baseline configurations, which were the tank type, were both at both sites. They both had single tank type water heaters, and site 1 had an A.O. Smith model with an input of about 199,000 BTUs per hour and an efficiency of about 0.8. It also had a recirc loop operating 24/7, and the storage volume was 100 gallons. The baseline system at site 2 was a remodel with an input of 250,000 BTUs per hour, the same 80% efficiency, and a similar 24/7 recirculation loop, and the capacity of that unit was 86 gallons. The combined condensing water heating systems that replaced the baseline systems for site 1 was made up of 4 units, and they were mounted back to back. They were all Rinnai model units with 96% efficiency. The input ratings were 199,000 BTUs per hour on the high end, and it could modulate or turn down to 15,200 BTUs an hour, which is approximately a 13-to-1 turn down ratio. Site 2 had the same make and model Rinnai units, but it had only 3 units that were mounted on the wall instead of mounted on the rack. So now I'd like to turn it over to Alex, which would go through the data analysis in detail.
Hello, everyone. Thanks, Rich. Today I will be going over the details about the field study that we conducted, as well as our monitoring approach. Also, some results for each test site and surveys that we conducted. So this diagram shows the baseline monitoring strategy used for both field sites. A detailed monitoring package was deployed to capture 1-second data for all of the parameters shown in this diagram. So the input to the system was measured using a gas meter to measure gas consumption, and a power meter measured any electric use of the system. Various system temperatures and flow rates were recorded to calculate the system output, as well as any water usage and recirculation operation. This diagram shows the monitoring equipment installed on our rack system. As you can see here, this is a 4-unit rack, which matched one of our test sites. That was site 1 that Rich was mentioning earlier. So flow meters and immersion temperature sensors were installed at each individual unit, while the main system instrumentation was left in place from the baseline monitoring period. And that includes the main flow meters and temperature sensors for the system and the recirculation loop. So input and output from each unit were measured, as well as the input and output for the entire system. And by measuring at an individual unit level, this really gave us a better understanding how each unit operated and cycled during operation. For a little more detail on our monitoring equipment, here's a quick summary of the main equipment we used to measure various parameters like water flows, gas consumption, and various temperatures throughout the system. So we used a combination of high precision RTD temperature sensors and thermocouples, gas meters to measure gas consumption at a unit level, and then water flow meters throughout the system to capture various water flows. As you can see in this detailed diagram shown here, this really shows the location of the thermal wells. So thermal wells are the fittings used to place our immersion temperature sensors within each pipe to get really accurate water temperatures. These were placed on the inlet and outlet of each unit. So the picture on the right shows the piping done by the contractor before the actual system was installed. This was required for our monitoring equipment, and you can really see the amount of additional piping that was done before the system was actually installed. So the existing tank type water heater from site 1 was located in a small mechanical space, which was too tight to place the actual rack system in. So you can see this in the picture on the left. It's not an amazing picture, but basically there are walls surrounding that tank very tightly, and it simply just wasn't feasible to put the rack system in that location. Because of that, the rack system was plumbed to an adjacent room that was large enough to hold it. And since there wasn't enough wall space to mount the rack, it was placed in a 2x2 kind of a back-to-back configuration shown on the picture on the right. Now the rack system for site 2 was placed in the same location as the existing tank. So this was a mechanical space that also contained the boiler used for space heating in the building. And this was certainly more of a traditional installation for these systems. So when we think of a rack, generally they're placed kind of side by side and mounted on a wall. And this is done to free up space in wherever it's going. So the 3-unit rack was able to mount nicely to the wall to do this, and due to the location of some of the boiler controls. So you can kind of see it on the picture on the right, there are some boiler controls. They did have to be shifted to accommodate the rack system. And again, these pictures really show the level of monitoring that we did at each site, and the system certainly looked far more cleaner when we were done with our monitoring period. So there was definitely a lot of additional piping needed for our equipment. So this plot shows the fluctuation of the incoming water temperature at each test site during our project. So each point on this plot represents the weekly minimum inlet water temperature plotted against the date. And you can really see the variation throughout each season, with a high peak around August or so, and then it bottoming out in roughly February. And since the Twin Cities area gets a lot of our water from the Mississippi River, this can vary the water temperature significantly and have an impact on how much energy a water heater uses. So colder water obviously needs more energy to be heated up, which will vary the energy input to each system throughout the year. In addition to that, when water is mixed at a faucet, colder inlet water, so think about in the wintertime, would require a higher percentage of hot water to mix it to the same temperature as it would when the inlet temperature is warmer, so in the summertime. So you can really see the impact that the water temperature has on water heating systems and how they actually operate. Here we have just a quick snapshot of a typical day of operation and water usage at one of our test sites. So this is site 1. Recirculation and outlet temperatures remain fairly steady throughout the day, and the inlet temperature fluctuates as there are more hot water draws. The pump for the recirculation loop runs constantly and shows a pretty steady water flow to provide tenants quick access to hot water. Overall, I'd say that the water temperatures and the flows remained consistent between the tank type system and the rack system. And ultimately, the rack units were able to maintain a very consistent supply water temperature throughout the project. So this plot shows the typical gallons per hour used for each site during each hour of the day. So both sites show a similar pattern with low usage overnight and an increase around, say, 6 or 7 a.m. And that's really for, people start waking up and start taking morning showers. So that's generally where those spikes occur. Usage remains relatively stable throughout the day with another moderate spike between 9 and 10 p.m. And this pattern of hot water use is relatively common for a multifamily setting like the 2 field sites that we looked at. So each of these plots show how an individual tankless unit operates at each site. So the left figure shows the 4-unit system at site 1 and shows the gas consumed versus the hour of the day. Each gas pulse represents a specific volume of gas consumed. And the real takeaway from these plots is to show how the system cycles and operates across each unit. So since there is a recirculation loop at each building that operates pretty much constantly throughout the day, there's always a constant draw of hot water throughout the building. By using a cascade setup, that's what they call a cascade setup, one of the units is set as the primary unit, and each additional unit is a secondary unit that's tied together with a communication cable. So with the primary unit acting as the controller, this connection will rotate water heater operation order to ensure equal usage among the entire system and enables all water heaters connected to modulate operation and function really as one hot water source. So by operating this way, this should really result in prolonged life of each unit in the system, assuming that proper maintenance practices are followed. So here we have efficiencies of each system for site 1. So we are comparing the baseline tank type unit versus the rack system. Efficiencies increase significantly from one system to the other, as well as the delivered capacity increases. So since both test sites were multifamily buildings, there was always a reasonable amount of hot water use. So the efficiency of the tank type system remains fairly flat. Past research has shown us that when the hot water use drops off and gets closer to 0. So think of a single family home where each point on this plot is a daily delivered capacity. So as if you're in a single family home where say someone doesn't take a shower or overall the hot water use is low, the efficiency of the system will drop off and get closer to 0. Ultimately, this shows the increased efficiency of the tankless units of the rack system as it can reach above 90% or so. And overall, the rack system efficiency is 10 to 15% higher than the baseline. So data from both test periods, the baseline and the racked period, was analyzed to determine annual energy consumption and efficiency. Each one of these plots shows the results from Site 1. Since there is a good amount of seasonality for each of these sites, it must be addressed in the data analysis. So weekly average delivered energy was plotted against the cold inlet water temperature. That's the plot on the bottom right. And this was to determine the average daily delivered capacity for each system at the average inlet water temperature during the test period. So that value was then used to calculate corresponding energy consumption for each system using the plot on the upper left corner, and that was done to determine energy savings. We performed analysis for both, really two ways, for the entire system as well as the water heater only. The entire system includes the recirculation loop. So this is a loop that's constantly moving hot water throughout the building. So tenants really always have hot water quickly when they turn on a fixture. And then the losses associated with that recirculation loop. So since heat is lost as water constantly circulates throughout the building, overall efficiencies are low due to the recirculation losses. Overall, we found that the rack system showed a savings of about 8% for Site 1 and 18% for Site 2. Here we have the results of the analysis of only the water heaters. So this focuses just on the efficiency of both the tank type system versus the rack system. Overall, we can see much higher efficiencies when comparing it to the complete system. And this really highlights the high efficiency operation of the rack tankless units with efficiencies in the mid to upper 80s, which is consistent with past tankless water heater research. So savings come in around 7% for Site 1 and 18% for Site 2. So the maintenance of these systems is pretty much identical to a standard single tankless water heater. When comparing to a tank type system, there's certainly some additional maintenance that can prolong the life of each unit. So for a tank type system, generally the recommended maintenance is to drain a few gallons of hot water from the system to remove any sediment at the bottom of the tank. So due to the nature of how a tankless unit operates, there are a few preventative maintenance actions that are recommended. The main maintenance piece is to flush a solution of vinegar and water throughout the heat exchanger, and that's really done to prevent scale buildup. And this process is shown in the picture on the right. So it's a pretty straightforward process that can be done by really anyone that maintains the system. And in addition to that, there are also a few filters that need to be cleaned during the flush. So if an individual unit of a rack system fails or needs repair, it can be replaced or serviced on an individual basis. So while one unit is serviced, the other units in the rack will still function. And this really allows system maintenance to occur without shutting off the hot water to the building, which is certainly an added benefit. Also, failed units can be replaced individually. So this means that the entire rack doesn't need to be all replaced at once. So getting into some surveys that we conducted, building owners, tenants, and the contractor who installed both systems were interviewed really to get a better understanding of the overall impressions of the rack system compared to a standard tank type water heater. So they were asked about things like the quality of delivered hot water, how each system was maintained, the importance of the non-energy benefits that the rack system offers, as well as any challenges and complexities of each system that they wanted to highlight. So overall, building owners were pleased with the rack system. Their main concern going into the project really was the reliability of the system and its ability to deliver hot water at all times. And while this was a concern, it was really outweighed by the potential energy savings of the rack system. So there weren't any major complaints during the test period. and both the owners and tenants were pretty satisfied. Tenants were given a detailed survey that asked questions about things like hot water delay and fluctuation of temperature, running out of hot water during long periods of hot water use, maintaining a steady water temperature. And overall, our goal was for the tenants to not experience any sort of drop off of hot water quality from the tank type system to the rack system. So since a large tank of hot water offers consistent hot water, that is until the tank runs out of hot water, which is pretty rare for a multifamily property. This is something that we wanted to document. The survey results showed that the tenants were very pleased with the rack system, and most stating that they didn't notice a significant difference in the hot water that they were receiving. So the contractor we work with had not installed the rack system before, but definitely had experience with tankless hot water systems. The potential issues that the contractor brought up included space constrictions and venting of the exhaust, both of which were easily addressed during the installation. In general, they stated that these systems would save space in most installations, and overall, the contractor had a positive experience with the installation and the performance of the rack system. So I will throw it back to Rich.
Thank you, Alex. What I'd like to do now is review the assessment tool that we put together regarding the best practice design standards. So it's an informative tool, and the engine behind it is essentially calculations from sources that include ASHRAE Applications Handbook, ASHRAE Research, Transactions, ACEEE proceedings, California Energy Commission, and the like. So the idea is to use it on a comparative basis where you can select a certain building type and you can put in certain climate zones, which would then refer to certain mains temperatures. You can change the number of rooms, the number of people, the perhaps the demand, the water demand, set point temperatures. It has variations for recirculation loop efficiencies, number of fixtures, and the like. So we can go into much more detail later, but essentially the tool uses the field data from the recirculation loop to enhance these calculations. So we went ahead and there were equipment estimates, and they were based on local prices and labor costs that were incurred within the project. So for the baseline tank units were between $4,000 and $9,000. The condensing systems were between $6,700 and $11,000. Within the inputs of this tool, there are branch losses or recirculation efficiency. So that has a default value of 34%, and that was according to the field test data. There's 44% for a poorly insulated, poorly designed system, and 24% for a good system. Hot water usage tiers were based on Hunter curves, which are standard in the industry, found within the ASHRAE handbook, and they basically look at peak demand values versus the number of fixture units. There's also an option for usage rates, high usage being basically 25% above these curves, these Hunter curves, and low usage being 25% below these curves. Then by choosing a certain climate zone, there's certain climate zones available, determines the main temperature and the like. The utility costs were taken, they can be added personal design options, but we used, for comparative purposes, U.S. Energy Information Administration database, and we use 67 cents a therm and $10 per kilowatt hour. We went ahead and compared along certain building types, and for a standard building type, we used what is in the prototype building models for the U.S. Office of Energy Efficiency and Renewable Energy. So an example of the output, the example of the spreadsheet, at the very top is the building description and other model inputs. Then you can choose multifamily types, you can choose hospitality, schools and universities, or otherwise. And then it could be number of dwelling units or number of rooms. There can be estimated daily occupancy, say for an office building. And it can go ahead and calculate your fixture units, essentially by the Hunter curves. And or it gives you an option to put in custom fixture units. Then I mentioned the hot water recirculation efficiencies, pump sizes, a diversity factor, yes or no, and then hot water characteristics regarding usage level, thermostat temperature, from the water heater itself, and then the mains temperature. So the mains temperature is basically based on the chart to the right, which shows entering cold water temperatures based on climate zones and water temperatures. At the bottom of the top portion are the energy prices that you can input, and then it does the calculation on the output based on what it estimates for the demand, what it estimates for performance of a non-condensing storage unit, a condensing storage unit, a high efficiency unit, and then the combined condensing tankless water heating system. So it goes through that calculation and comes up with millions of BTUs of gas per day, and it compares it on a curve on the right. It does that by looking at certain 10-year cost of ownership, types of pricing, and payback periods. So for example, a model then, such as this, which is your basic, what they're calling your energy model for an apartment high-rise, would tell us within this tool that there are 80 units in this building, there's 10 floors, there's 8 units per floor, there's 950 square feet per unit, and there's also other information that we can touch on, which includes orientation and aspect ratios. The other information includes, for modeling, for energy modeling, thermal zones, wall construction, roof construction, air barriers, foundation types, HVAC system sizing recommendations, recommended efficiencies, control system set points, minimum outside air ventilation rates, fan schedules, water heating recommendations, and then it goes into things like zone characteristics, lighting loads, plug loads. But it does show, and this is for 75% of the building stock out there, the average size and number of people. So there's 199 people for this apartment high rise, and for this particular model, which includes 75% of the building stock in the United States. So we can use this on a comparative basis in the same way. Not all this information is necessarily for this particular assessment tool, but it's available if we enhance the tool or there's other energy calculations that need to be done. And in the end, we're using this overall building size. We're looking at room sizes, number of occupants. That's what's necessary for this particular tool. So what the prototype building is for a secondary school then is 2 floors, and it has a total area of 210,900 square feet, and it has 6,096 students. So that is the average. For a medium-sized office building, it's 3 floors at 56,600 square feet and 286 people. For a small hotel, it's 4 floors, 259 people. And then if we go ahead and put this information into this tool, we can then look at different building types with certain default settings. So if we just defaulted the recirculation efficiency, the hot water usage, and things like that, we come out with certain outputs such as this for the apartment high rise, in the same way for the secondary school, in the same way for office, a medium office building, a large office building. And we can tabulate that information. And what we find is, as far from the tool and these calculations, that school applications have shorter paybacks and smaller demand applications. So a payback less than a year, some school may have a payback less than a year based on these best practice calculations. And then a larger multifamily unit of 80 units might have a 7.5 to 8 year payback. And office buildings, as they change from 270 occupancy to 2,400 occupancy, we notice that the payback goes down. So what we're essentially seeing is, as the demand increases, the efficiency and payback decreases. So then if we were to look at the simple payback, as Alex mentioned, the savings at the field test site, it would be between 9 and 23 years, and we look at the tool based on certain calculations, and it's midway in between what we found in the field based on the therms calculated within the tool. So then what we found essentially is that the 2 sites during the 22-month field test period can be condensing combined tankless water heating systems, be successfully installed and operated in multi-unit applications in northern Midwest climates. It provided energy savings with no significant change in hot water delivery or complaints. The combined tankless water heating system can save energy over the storage systems. Alex mentioned 12.7% of energy consumed, 18% on one site, 7% on the other site. The system efficiencies for the first site were 57% in the baseline and 59% in the tankless water heating site, and 63 in the baseline and 73% in the second site. The measured water heater efficiencies are lower than the rated, as Alex mentioned. The particular results were then compared to existing baseline equipment, and we did extrapolate it to other building types and loading patterns based on specific design calculations typical within the industry. We went ahead and applied those to sizing that was developed in multifamily units, hospitality, and schools. The initial cost can be a significant hurdle for many properties. There is, however, a reduced footprint that was frequently cited for increased market share. A smaller footprint would benefit both new construction and applications, retrofit applications. The control sequence, the cascaded control system that Alex mentioned, I think is a benefit to longer life and unique to this particular system. And there is also the savings can be enhanced for this particular system by using well-insulated recirculation loops and perhaps the addition of demand control on those recirculation loops. Thank you. Appreciate your attention.
Great. Thanks, both of you, for the great presentation. If you have not already done so, please type any additional questions into the Q&A panel and send them to all panelists so we can respond to them. Laura, do you have any questions for Rich or Alex at this time?
Yeah, Kevin has a question. Kevin's question is, I would assume some significant water savings too from the instant transport of water on demand, rather than some traditional water heaters where it takes some time for water in the fixtures to heat up. So maybe you could talk about that, those concepts a little more.
Sure. So I think the recirculation loop in these buildings that we looked at is really kind of what would cause water savings, significant water savings. So that really allows for hot water to be available kind of instantly as you turn on the tap versus waiting, say 15 or 25 seconds or so without one. And while there are water savings, it wasn't something that we really quantified in this project, since our main concern was really focused on the energy savings of the system. So certainly water savings, can be a part of it, but again, not something that we really quantified.
All right. Question from Hannah. With continued maintenance, what is the average life expectancy of a tankless model?
So I would say kind of a good estimated average life is about 15 to 20 years or so. These tankless units have been around for a couple decades now, and I think we're starting to kind of realize some of those really longer lives compared to a tank type model. With a tank type model, average life, I mean, it varies significantly on kind of a case by case basis, but generally kind of the average life of a tank type is about 10 to 13 years or so. So in theory, the life of a tankless unit could be about double that of a tank type system. But again, it really does vary.
Thank you. From Dave, the rated efficiency of the units was in the mid-90s and the measured was in the mid-80s. Why was the measured the efficiency lower than the rated efficiency?
Yeah, so I think that really comes down to kind of a lot of research that we do. We generally find that rated efficiencies aren't really seen in practice. So when we do a lot of our field research and install these systems, we pretty much always find that the actual efficiencies are quite a bit lower in practice when installed in the field versus a rated efficiency, which a lot of times is done as kind of a steady state efficiency in kind of a lab setting. So when you factor in things, different usage patterns at different buildings, and really just, the way the systems are operated is different than in a lab setting. So kind of all of those things combined really, really show that efficiencies in the field are generally lower than kind of a rated efficiency.
Sure, thank you. Was the number of tankless units determined from the manufacturer's recommendation? Or did you find that the number of units could have been reduced, or were the number installed needed? So I guess probably
Sure.
didn't have the correct emphasis, but kind of what determined the number of units, and did you find that you had some flexibility there, or what went in?
Sure. Yeah, so we worked with a local mechanical contractor and Renai, the manufacturer, to determine the sizing of the system. So kind of like we mentioned, one of our sites was a 3-unit system and one was a 4. Ultimately, Renai has an online calculator where I recall it's really done by kind of the number of fixtures, and it's by counting the number of units and kind of estimating, number of fixtures. They can give a recommendation on how many units that are actually needed for the entire system. So we worked with that calculator, the contractor, and the manufacturer to come up with a number of units. It can be slightly flexible. I think in larger buildings, you might have a little bit more flexibility, and that certainly is something that will kind of impact payback periods. Obviously, if you add another unit when you don't necessarily need it, obviously that will increase the initial cost and affect the payback period. So there's some flexibility there, but ultimately you're working with the contractor installing the system and the manufacturer to really hone down on the exact sizing necessary.
Great, thanks. So the way the rack systems are controlled sounds really interesting. Could you talk about that in more detail?
Sure. So, the goal of these rack systems is to maintain a specific supply water temperature. So generally that's between 120 and, say 130 degrees. These rack systems will rotate the operation of the units so that the runtime hours of each unit remains the same. And they do this to kind of prolong the life of each unit. So, say one unit is doing 90% of the actual runtime versus all of the others are doing a small fraction. They want the opposite of that. So they want to rotate it throughout each unit so that the runtime hours will kind of remain roughly the same. So to do this, they use what they call this cascade approach. So one of the units is set as the primary unit during the installation from the contractor. And this is I watched our contractor install the system. This is a pretty straightforward thing to do. And then they use communication cables to kind of control all other units in the rack. So each other secondary unit is connected using these cables, and then the primary unit rotates the operation evenly across all other secondary units. So in theory, this should allow each unit in the rack to really extend its life.
Right, and then after a certain runtime for the first unit is expired, then the second unit will begin to fire, and then the second to the third to the fourth to the first. I think it's really unique in that respect. I think it's totally different than the tank concept, and I agree it should extend the life significantly.
Great, thanks. One more question. And if people in the audience have more questions, please go ahead and put them in. One more question. Do you think that COVID and the fact that the units in the multifamily buildings were likely more fully occupied during the day for the post retrofit period of your project as compared to the baseline or pre-retrofit, do you think that difference had any impact on your results?
Sure. So in general, I would say that COVID really didn't have a significant impact on the results. So based on our timeline, COVID lockdowns started kind of near the beginning of the racked test period. So that was in March of 2020. And because of this, we really would have expected that, with more people working from home, hot water use would have increased, but in reality, the overall water use slightly decreased. I think we can kind of attribute this to a slightly higher supply water temperature from the rack system, which led to more mixing of cold water to reach desired temperature. So long story short, really no major impact that we noticed for COVID.
Right. Well, thank you. I will turn it back over to Mary Sue for some closing comments.
Great. Thanks, Laura. Thanks, Rich and Alex, for your presentation, and you, Laura, for facilitating the Q&A. If you have any follow-up questions about the CARD project, please feel free to contact one of us. Our emails are on this slide. The recording of this webinar and the slide set will be available at the department's website in a few weeks, and the final report in probably a month or so. When available, you can link to either of these from the quick links on our Applied Research and Development webpage, as indicated on this slide. The department's R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out by going to the address at the bottom of this slide. Thanks for your participation today. We really appreciate your interest in CARD projects, and I want to take a minute here now to mention 3 upcoming webinars in March and April. On March 22nd, the Center for Energy and Environment will discuss energy savings opportunities for residential multi-zone distribution systems. And then on the 13th of April, the Center for Energy will be back to report on results of a 3-year DOE and CARD-funded project that demonstrated and assessed the energy and non-energy benefits from power over Ethernet technologies at 4 commercial institutional sites. Then on April 28th, Franklin Energy will join us to discuss the energy savings potential of network lighting controls and the challenges of deploying them in small businesses through real-world projects. You can keep abreast of upcoming webinars and other news related to the Minnesota Conservation Improvement Program by signing up for our SIP updates on our newsletter list or email list. You can use the link on this slide to do that. And in the meantime, feel free to contact me if you have questions or suggestions for the CARD program or CARD webinars. And as a final reminder, there will be a short evaluation that launches after the webinar. Please take a few moments to fill it in and let us know how we did. Thanks so much for your attention, and have a good rest of your day.